When you picture space, do you imagine fixed points, like pins stuck in a map? In reality, that's an illusion. In space, everything is moving planets, satellites, even the very ground beneath your feet. There's no absolute spot to park a spaceship. Everything is relative, constantly shifting at thousands of miles per hour. Orbital mechanics, the science of motion in space, tells us that positions are always described relative to something else, like Earth or the Sun. So, when we talk about where something is in space, what we really mean is, where is it right now compared to us? Surprised? You're not alone. Even seasoned engineers sometimes forget that space is a cosmic dance, not a static grid. Let's start with one of the most famous fixed spots, geostationary orbit. Imagine a ring, 0 miles above Earth's equator, where satellites orbit at exactly the same speed the planet rotates. The result? To anyone on the ground, those satellites seem to hover in place. This is called the orbital periodon revolution every 24 hours. It's prime real estate up there, and believe me, it's getting crowded. Why? Because every telecom, weather, and broadcast satellite wants a slice of that stationary sky. But here's a twist. That ring is minuscule compared to the vastness of space, making these slots incredibly valuable. Ever wonder why satellite TV dishes don't move? They're locked onto these geostationary satellites. But geostationary orbit isn't the only game in town. Enter the Lagrange Points, a set of 5 unique positions where gravity and orbital motion balance perfectly, allowing objects to hover relative to 2 larger bodies, like the Earth and Sun. Think of them as gravitational parking lots. Here's the technical term, gravitational equilibrium. At these points, the combined gravitational pull of 2 bodies and the centrifugal force of an orbiting object cancel out. Now you might be thinking, are these spots actually stationary? They're as close as it gets in our ever-moving cosmos. That's why they're in such high demand for telescopes, satellites, and ambitious space missions. So how do Lagrange points actually work? Imagine 2 massive objects, say, Earth and the Sun. As they orbit each other, their gravitational fields interact. At certain points, the forces balance out, creating regions where a much smaller object can stay put with minimal effort. We call this station keeping using tiny adjustments to maintain position. The key here is the Hill sphere, the region around a body where it dominates the attraction of satellites. The lone and LAF2 points, for example, exist just at the edge of this sphere. It's a delicate balance, like a marble perched on a hilltop, but with just a little push, you can keep it there almost indefinitely. The lone and L2 points are especially valuable. Lone sits between Earth and the Sun, making it perfect for solar observatories or solar weather stations. L2, just beyond Earth on the opposite side from the Sun, is where the James Webb Space Telescope now orbits. Why? Because L2 lets the telescope stay in Earth's shadow, shielded from the Sun's glare, crucial for sensitive observations. These points are not completely stable, but with a bit of station keeping, spacecraft can maintain their position. The concept of a quasi-stable halo orbit comes into play here, a path around 2 that avoids direct sunlight and thermal issues. It's the ultimate spot for peering deep into the universe or protecting Earth from solar mayhem. It's not just Earth and the Sun. Every 2-body system has its own set of Lagrange points. Earth and the Moon, Jupiter and its moon-siege pair generates these gravitational sweet spots. For instance, Jupiter's L4 and L5 points are home to thousands of asteroids called Trojans, forming stable clusters ahead of and behind the planet in its orbit. Here's a technical term for you: orbital resonance, where objects in Lagrange points maintain a fixed relationship with the primary bodies, dancing in harmony for millions of years. This isn't just theory, it's observable fact, shaping the architecture of our solar system. What can we actually do at Lagrange points? The possibilities are incredible. Imagine building solar shades at Lone to filter sunlight and cool the planet, or deploying giant mirrors at L2 to bounce light onto the dark side of a tidally locked world. Here's where the concept of a solar sail comes in: a vast, lightweight panel that uses radiation pressure to maneuver without fuel. These technologies could one day terraform planets, shield us from solar flares, or even regulate Earth's climate. Lagrange points aren't just theoretical curiosities, they might be the backbone of future planetary engineering. Let's focus on the L4 and L5 points, often called Trojan points. These positions form equilateral triangles with the 2 main bodies and are notably stable, hosting natural clusters of asteroids. Think of them as cosmic safe harbors. The term Trojan asteroids comes from Jupiter, but Earth, Mars, and even the Moon have their own Trojans. Now, picture future space colonies built at these sites-fast areas with minimal gravitational disturbances, perfect for massive habitats. Maybe you're wondering, could these become new frontiers for human settlement? It's more plausible than you might think, especially as low Earth orbit gets ever more congested. Now, let's stretch our imagination. What if we connected multiple Lagrange points with tethers, forming a vast network? Welcome to the concept of the Lagrange diamond. By establishing stations at Lone, L2, L4, and L5 around a body like the Moon, and linking them, we could create a stable, three-dimensional web for transportation, manufacturing, or defense. The technical term here is rotovatora, rotating space tether that can launch or capture spacecraft with minimal fuel. This isn't just sci-fi. Such networks could revolutionize how we move cargo, build megastructures, and even launch missions deeper into the solar system. Ultimately, Lagrange points offer more than just scientific curiosity, they're the prime real estate of the cosmos. Imagine a future where thousands, even millions, live and work in massive habitats anchored at these stable islands in space. Unlike the crowded, high-speed chaos of low Earth orbit, Lagrange points provide safety from debris, cascades, what's known as the Kessler syndrome. They're the river valleys and harbors of the new space age. As Earth's orbit fills up and humanity expands outward, these points will become hubs of innovation, commerce, and maybe even culture. So, next time you look up, remember, the future of space settlement may hinge on these rare, hidden gems where gravity and motion cancel out, and opportunity hangs in the balance.